Experimental investigation on self-compacting concrete by replacing industrial waste materials. Abstract. Due to versatility of concrete as a construction material, it is utilized in large quantities over the world. Self-compacting concrete is an innovative concrete which does not require any vibration and gets compacted on its own weight. To check the feasibility of utilizing different waste materials and industrial byproducts in concrete, extensive research has been carried out to develop high quality and grade of SCC. This paper reviews the influence of utilizing such waste materials as partial replacement of cement and the performance of SCC in both fresh and hardened state. Its durability aspects were also considered. Keywords: self-compacting concrete, nanosilica, microsilica, acid resistance, sulfate resistance test, acid resistance test. This self-compacting concrete, SCC, was first developed in Japan, in the mid to late 1980s, as a means to create uniformity in the quality of concrete by controlling the ever-present problem of insufficient compaction by a workforce that was losing skilled labor and by the increased complexity of designs and reinforcement details in modern structural members. Durability was the main concern, and the purpose was to develop a concrete mix that would reduce or eliminate the need for vibration to achieve consolidation. Self-compacting concrete achieves this by its unique fresh state properties. In the plastic state, it flows under its own weight and maintain homogeneity while completely filling any formwork and passing around congested reinforcement. In the hardened state, it equals or excels standard concrete with respect to strength and durability. The use of SCC concrete has been increasing in the United States also during the last 5 years. Currently the technology is being primarily applied to the precast industry. Other segments being targeted are flatwork, columns, and wall construction. The applications of SCC are many, limited only by the industry's knowledge of it, ability to produce it and acceptance of it. The usual self-compacting concretes have compressive strengths in the range of 60-100 N/mm superscript 2. However, ultra-high performance self-compacting concrete, UPC, with strength about 150 N/mm superscript 2 has also been successfully developed. The durability of cement concrete is defined as its ability to resist weathering action, chemical attack, abrasion, or any other process of deterioration. Durable concrete will remain its original form, quality, and serviceability when exposed to its environment. Literature review. Ever since the first report of the development of SCC in Japan in 1988 by Ezhilarasi et al. Using superplasticizers and viscosity against N in 1992, they again identified the factors controlling self-compacting, namely coarse and fine aggregate content, and presented the paper at Kenmet ACI International Conference, 1992, which spread the concept of SCC in the world. Admixtures et al., 2011, an experimental investigation into mechanical properties of self-compacting concrete inculpating fly ash and silica fume at different ages of curing. Self-compacting mixtures had a cement replacement of 20, 30, and 40% with Class F fly ash and 5,10 and 15% with silica fume. The results show that normal-strength self-compacting concrete could be successfully produced using fly ash and silica fume. Compressive strength after 28 days in mixtures containing fly ash is fairly balanced, with the result that specimens containing 30% fly ash along with 5% silica fume content develop compressive strength similar to the control mixture. Ezhilarasi et al., 2011, has investigated performance of self-compacting concrete containing different mineral admixtures. The influence of mineral admixture on a workability, compressive strength, ultrasonic pulse velocity, density, and sulfate resistance of SCC was investigated. Sulfate resistance tests involved immersion in 10% magnesium sulfate and 10% sodium sulfate solutions for a period of 400 days. Replacing 25% of PC with Fa resulted in strength of more than 150 MPa at 400 days. On the other hand, the best resistance to sodium and magnesium sulfate attacks was obtained from a combination of 40% GBFS, granulated blast furnace slag, with 60% PC. The pozzolanic materials Fa and GBFS increased the late-age compressive strength of SCC mixtures. Replacing 25% of PC with Fa resulted in a strength of more than 150 MPa at 400 days. Replacing cement with 40% GBFS can reduce magnesium sulfate attack by 1/3 when compared to control mixture. Kemoledin Yilmaz et.al. 2011 has investigated effect of mineral admixtures on properties of self-compacting concrete. Limestone powder, LP, basalt powder, BP, and marble powder, MP, are used directly without attempting any additional processing in the production of SCC. The water-to-binder ratio is maintained at 30% for all mixtures. The results show that it is possible to successfully utilize waste LP, BP, and MP as mineral admixtures in proceeding SCC. The addition of limestone powder, LP, basalt powder, BP, and marble powder, MP, had positive effects on the workability. Static and dynamic elastic moduli also increased, and the higher static elastic modulus and dynamic elastic modulus have been obtained for MP20 and MP10. C.Selvamoni et.al. 2010 has investigation on self-compacted self-curing concrete using limestone powder and clinkers, which the use of silica fume in concrete increased the dosage of superplasticizers. At the same constant SP dosage 0.8% and mineral additive constant 30%, LP can better improve the workability than that of control and fine aggregate by 5% to 45%. A maximum of 8% of limestone powder with silica fume, 30% of quarry dust and 14% of clinkers was able to be used as mineral admixtures without affecting the self-compatibility. The silica fume was observed to improve the mechanical property of SCC, while limestone powder along with quarry dusts affecting mechanical properties of SCC. S. Venkutswara Rao et.al. 2010 has investigation of effect of size of aggregate and fines on standard and high-strength self-compacting concrete. The mechanical properties viz., compressive strength, flexural strength and split tensile strengths were studied at the end of 3, 7, and 28 days for standard and high-strength SCC with different sizes of aggregate. It was noted that with 10 mm size aggregate and 52% fly ash in total powder, the mechanical properties were superior in standard SCC, while 16 mm size aggregate with a 31% fly ash in total powder improved the properties of high-strength SCC. Size of aggregate was 10 mm for standard self-compacting concrete, M30, while it is 16 mm for high-strength self-compacting concrete, M70, though all other sizes. Optimum dosages of fly ash were 52% addition in case of standard grade SCC, and it is 31% addition in case of high-strength SCC. 2. Methodology. In this paper, self-compacting concrete is made by replacing cement with microsilica and nanosilica. These materials were collected and replaced with ordinary Portland cement. Basic physical, mechanical properties and chemical compositions were tested for the mix design. Mix proportions were designed based on FNARC guidelines. Fresh concrete and workability tests were done for SCC as per code guidelines. In order to study about durability properties, few laboratory tests were done, like water absorption and acid resistance. 3 properties of materials. A. Portland cement concrete. The Portland cement usually takes several hours to set, and will harden in a matter of weeks. Cement is a somewhat curious material in that it continues to harden over time as long as there is water available for the components of the cement to form bonds with. 1-week-old Portland cement has strength of around 23 MPa, whereas 3-month-old cement has a strength of 41 MPa. These numbers apply to standard Portland cement, which has not had any additives added to it. Various treatments and additives can make cement set and harden at different rates, and various types of Portland cement also possess different properties which affect the rate of setting and hardening. B. Aggregates. Crushed angular granite metal of 20 mm size from a local source was used as coarse aggregate. River sand was used as fine aggregate and was used in the investigation. C. Superplasticizer. Glenium B233 consists of a carboxylic ether polymer with long side chains. At the beginning of the mixing process it initiates the same electrostatic dispersion mechanism as the traditional superplasticizers, but the side chains linked to the polymer backbone generates a steric hindrance which greatly stabilizes the cement particles' ability to separate and disperse. Steric hindrance provides a physical barrier, alongside the electrostatic barrier, between the cement grains. With this process, flow-able concrete with greatly reduced water content is obtained. The optimum dosage of SP should be determined with trial mixes. Table 1 Properties of materials. Material properties. Ranges. D. Admix Tuesday. The concrete mixtures investigated in this study were prepared with Portland cement type 2, microsilica powder and nanosilica. The specific gravity of microsilica and nanosilica is 2.17 and 1.03, and they are silica particles with a maximum size of 0.2 m and 50 nm, respectively. In addition, nanosilica is a water emulsion with 50% of dry solid and pH of 10. The control mix which was exclude of microsilica and nanosilica. V mix proportions. Design strength of SCC equals 50 MPa. Aggregate size equals 12 mm. Specific gravity of coarse aggregate equals 2.86. Bulk density of coarse aggregate equals 2018 kg/m3. Specific gravity of fine aggregate equals 2.703. Bulk density of fine aggregate equals 1567 kg/m3. Specific gravity of cement equals 3.15. Volume ratio of the fine aggregate equals 54%. Volume ratio of coarse aggregate equals 46%. Superplasticizer specific gravity equals 1.064. Air content in SCC equals 2%. Conventional mix. Cement equals 485 kg/m3. Fine aggregate equals 995 kg/m3. Coarse aggregate equals 1114 kg/m3. Superplasticizer, 2% of cement, equals 9.7 kg/m3. Water equals 156 liters. 6. Experimental investigation. A. Fresh concrete test results. Several test methods have been developed and together with visual inspection are often utilized to verify the performance of fresh SCC. However, none of these methods are standardized as yet, either nationally or internationally. Some of these test methods include the slump.out test, funnel test, U-type and box-type tests, T50 test, J-ring test. Using nanosilica in SCC individually there is no greater differences in strength gaining as compared to conventional concrete, but it has improved the flexural strength up to 5% using 3% of microsilica. The concrete with addition of 15% microsilica, based on the mass of cement, in SCC, the compressive strength, split tensile strength, flexural strength increased by 22%, 25%, 19% respectively. The comparison results of microsilica, nanosilica, combination of microsilica and nanosilica specimen indicated that a more suitable and strength gaining in SCC is combination of microsilica and nanosilica, that is concrete with combination of 15% of microsilica and 3% of nanosilica improve the compressive strength, split tensile strength, flexural strength by 25.61%, 25%, 19% respectively. See durability test on concrete. The ability of this SCC along with the various admixtures are tested for its ability to resist weathering action, chemical attack, and abrasion. The test on durability varies based on its environmental conditions. Here we check with the following tests. 1. Saturated water absorption test. The engineering properties of SCC such as saturated water absorption, sulfate resistance, acid resistance improved while designing 15% of microsilica with 3% of nanosilica. 7. Conclusion. Based on experimental research for 3 self-compacting concrete mixes, only microsilica, nanosilica, combination of micro and nanosilica, the following conclusions can be drawn at 28 days. Due to observed workability and high flowability of SCC, it can be used in highly congested reinforcement structure as compared to conventional concrete. Using nanosilica in SCC individually, there is no greater differences in strength gaining as compared to conventional concrete, but it has improved the flexural strength up to 5% using 3% of microsilica. 3. The concrete with addition of 15% microsilica, based on the mass of cement, in SCC, the compressive strength, split tensile strength, flexural strength increased by 22%, 25%, 19% respectively. As a general conclusion, the comparison results of microsilica, nanosilica, combination of microsilica and nanosilica specimen indicated that a more suitable and strength gaining in SCC is combination of microsilica and nanosilica, that is concrete with combination of 15% of microsilica and 3% nanosilica improve the compressive strength, split tensile strength, flexural strength by 25.61%, 25%, 19% respectively. 5. The engineering properties of SCC such as saturated water absorption, sulfate resistance, acid resistance improved while designing 15% of microsilica with 3% of nanosilica.